Welcome back. It's Eric Hyatt again with another video from Oceanography for my Oceanography course 328-528. And today's topic is the second part of ocean basins. And it's a very interesting topic because it deals with the composition of the crust and the formation of the ocean basins and tells us a lot about how the Earth works. So let's get going. So ocean basins and plate tectonics. Ocean basins, first part of this section, and we started out last time with early beliefs and discoveries that led to understanding of ocean basins, and also, as you'll see, is a big component of where plate tectonic theory came from. We talked about Marie Tharp's discovery when she was mapping the profiles and the depth data from sonar analyses of especially the Atlantic, but all the global oceans, and she made these similar kind of profiles to these, and it showed in the case of the Atlantic that there's this interesting valley in the center of the mid-ocean ridge, and we know that today as the axial valley of the mid-ocean ridge. And then she interpreted, as I mentioned last time, that there was one in the East Pacific Rise in the Pacific, but actually it doesn't have one, we know now. So the East Pacific Rise is spreading about twice as fast as the Atlantic, and so it's much more diffuse, and it doesn't have that well-developed axial valley in the center, but it is high and broad compared to the mid-ocean ridge in the Atlantic. I spoke to you about the East African Rift and the study of that system in the 1960s particularly and into the 70s, and how that was used an analogous setting to the mid-ocean ridges, the spreading that's going on in the mid-ocean ridges. This view, looking onto the African continent down the axis right here of the East African Rift, shows us the broad uplift that occurs as rifting happens underneath the continent, but also it shows the Rift Valley, and you see these fault scarps coming down at kind of high angles into the Earth's surface as this valley spreads apart. And this was used as the analog for the mid-ocean ridge rifting. Our next step in the journey of understanding the discoveries that led to plate tectonic theory and understanding the ocean basins is the data that came from thickness of the sediments on the seafloor and the age of the ocean crust. These discoveries came from the ocean drilling program, first with the Challenger drill ship and then later with the JODI's Resolution. But for the first time, we were able to drill into the sediments and then later the crystalline ocean crust of the seafloor. And the first thing that came out was the discovery that the sediment thickness on the ocean crust in the deep ocean was thin at the mid-ocean ridges, and it got thicker as you moved away from the ridges toward the continents. The second aspect was actually sampling the basalt, and then eventually, it's a very difficult problem, but eventually getting enough radioactive minerals out of the basalt, uranium-bearing minerals in particular, that could be dated with uranium-lead dating to determine the actual numerical age of the basalt seafloor. And the amazing thing that came out of that was the ocean crust at the mid-ocean ridges is much younger, the youngest, and then as you move away from the ridges, symmetrically about the ridge, the ages get older and older as you move away. So the ocean drilling program gave us an insight and a window into the history that was recorded on the seafloor. And as I mentioned to you, originally it was hypothesized that the ocean basins were persistent and largely unchanged throughout Earth history, and thus should contain a complete record of sediment of the whole history of the Earth on the seafloor. The ocean drilling program allowed us for the first time to have a window into those sediments, and what we could see for the first time was the distribution of sediments and the relatively thin layer of sediments in much of the oceans on the crystalline basaltic ocean crust. So this diagram shows the JORDI's resolution sitting at the sea surface, and a drill stem going down to the seafloor and drilling into the sediment and the crust. And an example of some of the discoveries that came out of those ocean drilling program studies early on was this red zone, this red layer of sediment. That's the Cretaceous Tertiary boundary. So the yellow arrow there points to the moment of extinction for the dinosaurs and the transition, the immediate transition into the Tertiary. So the Cretaceous sediments below, the red zone is oxidized meteorite impact ejecta that fell to the seafloor and has become oxidized, and then the overlying darker gray layer is the aftermath of the KT boundary extinction, and that's Tertiary age sediment here. And if we look at the global distribution of sediment on the seafloor today, what you can see, the thickness is shown here in thousands of meters, and the reds, oranges and reds and dark red, are very, very thick sediment, up to 10 kilometers or more. And then the thin sediment is this dark blue. And what you notice is the thinnest layer of sediment, just a few hundred meters deep, is in the center of the ocean basins. And generally, if you focus on the Atlantic, you get an interesting pattern. And this sediment actually thickens up right on top of the mid-ocean ridge a little bit. And that's biochemical sediment. That's calcite, calcium carbonate. And then as you go into deeper areas off the ridge, this is the thinnest covering of sediment. And then it systematically gets thicker and thicker as you approach the continent, and to the point where it's many kilometers thick along the continental margins. So this is an interesting pattern that we see in some areas. We see it here in the North Atlantic Ocean Basin, and we see a streak of sediment piled up on the deep ocean seafloor in the Pacific. And that, again, is a biochemical sediment that's built up due to the equatorial wind system. And so there are some interesting variations, exceptions to the rule of thinnest sediment on the mid-ocean ridges and thicker sediment as you move away with older and older ocean crust. But generally that relationship holds up. Drilling through the sediment and collecting samples of basalt underneath the sediment allowed geologists to extract enough uranium from the basalt in a few places at first. Because of the difficulty of extracting enough uranium from the basalt, there were very few data points at first. In the 1960s and 70s, finally, with better technology, with more sensitive instrumentation that didn't require as much uranium and lead to measure to actually get a uranium-lead age, scientists were able to piece together more and more of the data points, and from the data points to extrapolate bands of ages. And if you look at the Atlantic again, the Atlantic provides a really nice symmetrical pattern because the mid-ocean ridge is basically right in the center of the ocean basin. It's a much younger ocean basin than the Pacific. The youngest volcanic rock that makes up the basalt of the seafloor is right in the axial valley of the mid-ocean ridge. And as you notice, the colors change from these reds, yellows, oranges to blues and greens as you move away from the mid-ocean ridge. So you're going from essentially modern basalt forming in the last few hundred years in the axial valley of the mid-ocean ridge to slightly older and older and oldest to the very oldest ocean crust near the continent in North America, near the continent in North Africa, and then there's a big area of old ocean crust over here in the West Pacific. And what you see is quite interesting. The oldest ocean crust is Jurassic in age. So the age of Brontosaurus, the age of the early dinosaurs. There isn't ocean crust today from the Paleozoic, for example, let alone the Precambrian. So this is a very small, maybe the last 10, 12% of Earth history is recorded on the seafloor of the world's oceans. But when we plot up the distribution of ages around the world, you see something interesting. You see this nice symmetrical pattern about the mid-ocean ridges, but you also see the activity on the mid-ocean ridges, or the rate of spreading on the mid-ocean ridges. In the Atlantic, the spreading rate is relatively slow, so on the order of 2 to 3 centimeters per year. That is about what? An inch and a half per year. Pacific, the rate is double that. So the rate in the Pacific, on the East Pacific rise, is about 5 and even up to 6 centimeters per year. And the result of that is you see wider areas of the same colors that you see in the Atlantic. For example, this yellowish tan color is much narrower in the Atlantic and very wide in the Pacific. And it tells you that the spreading rate, the creation of that seafloor, that ocean crust, is much faster than that being created in the Atlantic. This video graphic, basically what's happening here, time is running backwards, and we're putting the ocean crust back into the mid-ocean ridges. So we're essentially forcing it back into the mid-ocean ridges. And you see here's Cretaceous. This is what existed during the Cretaceous. The North Atlantic is closing up. The North Atlantic opened first, and then the South Atlantic. Now we've reached the Triassic and beyond. Now we're into the Paleozoic, and you notice there's no color on the seafloor. And there's no color because that seafloor, that ocean crust, doesn't exist. So there's no ocean crust before the Jurassic that's preserved. We know where the position of the continents were. We know the continents were moving around based on magnetic minerals. Here's another view, like a global view of the Earth. As again, we put the seafloor and the ocean crust back into the mid-ocean ridges. And this is focused on the Atlantic again. You'll see the South Atlantic closes first, and then eventually the North Atlantic closes down. But we know the position of the continents because of the magnetism in minerals in the continents act like kind of paleo compass needles that we can measure, and we can determine where they were in terms of latitude especially. Longitude is a little bit more difficult, but we can still do that with some accuracy. Now Wisconsin and North America, finally, you see there at the Paleozoic, the early Paleozoic was south of the equator and kind of in the tropics. All right, the next topic is the composition of the ocean crust, and that's igneous rock called basalt. Okay, British people pronounce it basalt. We pronounce it here in America, we pronounce it basalt. And it's a fine-grained, dark, black, igneous rock that forms from rapid cooling near or at the Earth's surface. It cools in the matter of hours to years and maybe decades. So the crystal size is quite small. So for scale, these are millimeters here, and you can make out a little bit of speckliness to this sample. This is a sample that I collected from Antarctica, along with these other samples with bubbles and gas bubbles frozen in it. And it's also a lot. These samples are, some of them, this one in particular is shiny from being polished by wind abrasion, like fine-grained, sandy, dusty sediment blowing against it, making it polished. But these little speckles are millimeter and sub-millimeter size crystals that make up the rock. So it's crystalline, it's very fine grain, it has crystals in it, but as you'll see, much of the matrix could actually be glass or glassy. So it's not fully crystalline much of the time. And in fact, these shiny samples down here are very glassy. There may be very few minerals. We'd have to look through a microscope to see if there were any minerals in there, but they cooled so quickly that they're probably mostly glass. So crystals didn't have time to form. So basalt forms from volcanic activity extruding onto the surface of the Earth. This is a picture from Hawaii with a lava kind of fountain spraying out magma that's 1200 degrees plus, and it's cooling very rapidly, getting a glassy surface on these black surfaces and flowing very easily downhill. And it'll eventually slow down and cool and become basalt. And pretty much the whole island of Hawaii is made of basaltic volcanoes. And this is Diamond Head for reference in Honolulu. Waikiki Beach is right here. And it's a beautiful spot. It's a beautiful place to live. Hawaii is basaltic volcanoes. Let's look at basalt composition first. Overall, in terms of elements, chemistry. Oxygen is the #1 element by weight in basalt, and silica, aluminum, calcium, and iron, magnesium, sodium. A little bit of titanium, maybe 0.5% is pretty typical, maybe 1%. But the surprising thing is oxygen by weight is still #1 even in the ocean crust, even in basalt. It's more in the continental crust, but even in basalt, it's #1. In terms of the mineral composition of basalt, by far the #1 mineral in basalt is calcium-rich plagioclase feldspar. Sometimes the mineral name is called anorthosite. That's calcium, aluminum, silicate. The 8. Get that? And then there's a black mineral, and the family name is pyroxene. The most common variety is augite. It's a black with a slightly greenish tint to it, mineral that's pretty chunky and hard to identify sometimes. It's calcium, sodium, magnesium, iron, aluminum, and silica and aluminum with 6 oxygens tied to it. The aluminum might be fairly low concentration actually, but those other elements will be there. Olivine is sometimes there. It's a green mineral. Olivine is olive green. It has magnesium and iron to various amounts tied to a silicate tetrahedron, that SiO4 building block of silicate minerals. And then there's a black, opaque, magnetic mineral called magnetite. It's iron oxide, but it's a fairly low component concentration in basalt, usually a fraction of 1 weight percent. If we take that same composition that makes up basalt and let it cool very slowly, we get coarsely crystalline textures like this one. Each one of these larger crystals like this one is about 1 centimeter across. We say this is a mafic composition for magnesium and iron rich. Mafic magnesium, and the Fic part is ferrous or ferric iron. And so it's magnesium and iron rich composition. And if you saw this as like a polished slab or polished stone at a store like Home Depot, they would call this black granite, but its actual name is gabbro. So its true name is gabbro. It's a very different rock than granite. It has no quartz in it. It's all made of plagioclase feldspar. That's what these long crystals are here. And this is a plagioclase feldspar also, probably looking at an end-on view of one. And then the black areas, the big black areas here, are the mineral family, pyroxene. And as I mentioned before, the specific common mineral in that family that you've maybe heard of before is augite. So where does this material come from? It comes from a mantle source, and it's the upper mantle, and the upper mantle then is separated into the lighter elements in the upper mantle from this starting material of the upper mantle. And the upper mantle is green. If it forms a rock, it's called peridotite. Maybe you heard of that term before, peridotite. The upper mantle has an olivine rich composition. And if you take this olivine and let it form a large crystal, a large beautiful crystal that's gem quality. In fact, you maybe heard of the gemstone peridot before, peridot. And peridot is just a crystal of olivine. And a rock that's made up of mostly olivine is called peridotite or peridotite, peridotite. And that's what this is, peridotite xenoliths. And a xenolith is a foreign rock. Like xenophobia, you're afraid of foreigners. Xenolith is foreign rock. You could have a xenolithic phobia. How about xenolithic phobia? you have a fear of foreign rocks instead of just foreigners. Okay, and it's encased in this example in basalt, and the basalt's got bubbles in it and things like that, but it's got fragments of the upper mantle that were carried up in this volcanic eruption. It has carried up fragments of this foreign rock, and the foreign rock is peridotite, which is, it's not really, in a way, a foreign rock. It's what the basalt was actually derived from. The basalt is the lighter material separated off of the peridotite. And this is the classic mafic composition. So basalt is mafic composition. And in fact, we often say that the peridotite layer is ultra-mafic. It's beyond mafic. The mafic composition is separated out from the ultramafic, the peridotite. If we look at a classification system for igneous rocks, you see over here there's peridotite, that nice green rock made of olivine and maybe some pyroxene. If you go to the left on this diagram, we have gabbro and basalt. So now we've moved from ultramafic to mafic composition, and now we have calcium-rich plagioclase, which is anorthosite. We have pyroxene. We could have some amphibole or hornblende. We could have some olivine present also. And as we go more and more silica, so silicon and oxygen and aluminum rich, we get to rocks that you've heard of before. Granite, for example. Pink potassium feldspar, gray glassy quartz, white sodium rich plagioclase, and biotite, and maybe a little bit of hornblende would be the black minerals. So you know that. You don't need to know this diagram, but it kind of sorts out which minerals fall where. And the ones that would be good to know would be granite with, because don't take it for granted, potassium feldspar, quartz, white sodium-rich plagioclase, and biotite, and then contrast that to basalt with calcium-rich plagioclase, maybe some hornblende or amphibole, but a lot of pyroxene or augite, and maybe a little bit of olivine. So those two end members would be good to think about and have a feel for in terms of what makes them different. So let's dive in a little bit closer and look at a microscope view of basalt. And it tells us some really interesting facts about basalt and how it's put together. So for scale, here's a 0.5 millimeter, and this is the same view in two different kinds of light of a basalt sample. It's the sample one of the samples that we use in 102 labs in Harrington Hall. I took one of those samples and just made a microscope slide from it, slice it down, it's no big deal, sliced it and made it 30 microns thick, and then light goes through it very nicely. And this view, light is just passing straight through the sample, and what we see here are blade-like crystals, different orientations. This one's probably coming out, the blade is kind of coming out towards us, but these are calcium-rich plagioclase, feldspar. And you can make out some striations here, some linear patterns on them. And the other big component that is really inconspicuous at first is all this brown material around all these little tiny needles of plagioclase feldspar is glass. So this is volcanic glass. The calcium-rich plagioclase feldspar crystals are they're swimming in a sea of brown glass. How weird is that? About half of this rock or more of this basalt sample is actually glass. And you'd never know it looking at the actual rock sample. It just looks black and very fine grain, but it's actually not even crystalline. Much of it's not even crystalline. It's actually volcanic glass. These dark areas here that look pretty equant and almost like little squares, or they're actually little octahedral shapes, those are magnetite crystals inside the basalt. And that's very typical for how much magnetite is in basalt. So keep that in mind, because this is going to be very important. Some of the other crystals in here, this is probably pyroxene. It could be a little tiny fragment of olivine. It's kind of hard to tell on this sample. But this view in this pair is actually looking at cross-polarized light, so no light should go through the sample. through the thin section, through the microscope slide, except light that's been twisted by a crystal structure. And so the glass does not twist, doesn't have a crystal structure, so it doesn't twist the light, and so no light passes through the glass. It's passing through these crystals, and depending on how much twist of that light, those rays of light, it can affect the color, and so we're getting a bright greenish bluish color here. From that brightness looks like olivine, but the crystal actually looks a little bit more like a fragment of pyroxene or augite. But the plagioclase feldspar is standing out very nicely. You can see its striations right there very well. And this little guy down here is augite or pyroxene of some kind. So it's hiding out right here. And we couldn't tell that from this view, but with that pinkish kind of blush color, that is very characteristic of pyroxene or augite. Here's a magnified view of that same sample with the large calcium-rich plagioclase crystals and then the small versions of them looking like little needles all through this brown, gray, glassy matrix. And then again, here are those equant magnetite crystals. The magnetite is going to play an outsized role in interpreting and understanding the nature and evolution of the ocean basins and plate tectonic theory. Who knew? These little tiny crystals of magnetite are going to be very important players. And when basalt like that sample cools, the magnetite crystals actually develop a preferred orientation that align with the Earth's magnetic field.